Hello, robotics community. Welcome to our talk. I'm Tianjian Chen from Columbia University in the United States. Today, with my colleague Tianyi, I will be presenting our work on underactuated hand design paradigms leveraging spring agonists. As a background, this project is supported by NASA. The ultimate goal is to design a compact hand for the Astrobee robot in the International Space Station. The Astrobee is a free-flying assistive robot. In addition to providing extra eyes and ears in the space station, we also aim to enable it to offer extra hands. The hand for Astrobee needs to be versatile to grab a variety of food and tools for astronauts. It also needs to be very compact and stowed inside the payload bay of this robot, shown in this white box. Besides, it should also be energy efficient and human safe. In this project, we aim to deliver not only engineering prototypes to meet these requirements, but also design methodologies. One solution to versatility and compactness at the same time is underactuation. There are a tremendous amount of work in this domain of underactuated, especially tendon-driven underactuated hands. However, the design space is huge. In this work, we aim to investigate some underexplored tendon underactuation paradigms. Before the details, let me introduce the terminology we used here, agonist versus antagonist. Basically, for a human or tendon-driven robot joint, the tendon or muscle generating the motion of interest is called agonist, and the counterbalancing tendon or muscle is called antagonist. In one-way tendon transmission shown in the middle, we usually replace the antagonist tendon by a spring. However, the opposite way, which replaces the agonist by below the spring, is rarely explored. Another design choice is the tendon routing scheme across multiple joints. We can either have one tendon going through multiple joints, or have one tendon for each joint, but have all tendons merging together on a motor shaft. When we combine the choice of agonist versus antagonist with tendon routing scheme across multiple joints, we can form this two-dimensional design matrix. The upper left is the most commonly used paradigm in underactuated hands. It uses an actively controlled tendon as an agonist and a restoring spring as an antagonist. It has properties such as pre-contact position coupling, post-contact torque coupling, differential or breakaway behavior between joints, and joint torque regulation capability. The upper right uses tendons on the backside of fingers and use preloaded springs as agonists. This is rare in robotics since it is hard to regulate grasping forces, but common in harness-driven hand prosthetics or hooks because it can still hold the grasp in the absence of active motor torque. The bottom left, which has independent agonist tendons, is also rare because it does not have the differential or breakaway behavior between joints. The bottom right, with independent antagonist tendons and preloaded agonist springs, is underexplored but of particular interest. It can provide differential or breakaway behavior via tendon slack. When any joint is blocked, its tendon can get slack and the motor can keep rotating and other joints can keep moving. It also has position coupling before contact, but allows the decoupling of joint torques after contact. Therefore, this paradigm is especially useful when joint torque coupling is undesirable. For example, we don't want finger adduction torque coupled with flexion torque in grasping. Next, we will show our design combining the two paradigms on the diagonal. Here is the design, combining the aforementioned two tendon paradigms in red and orange. The red tendons are for flexion, and they are in the classical paradigm which uses tendons as agonists and has multiple joints along one tendon. The orange tendons are for abduction-adduction, and they are in the springs as agonist fashion. and different adduction joints have independent tendons. Please note that the red and orange tendons are winded in opposite directions on the motor shaft. When the motor collects the red tendons, it releases orange tendons, and vice versa. In this way, the abduction motions still have position differentials. Also, deflection and abductions are still kinematically coupled before contact, but torque-wise decoupled after contact. We performed the optimization of the mechanically realizable manifolds introduced in our previous paper using this tendon routing, and got the transmission parameters. In this slide, we demonstrate grasps of different types and with different objects. Next, I will let Tianyi introduce another feature of this design, the spring force cancellation and its benefits.
Thanks, Tianjian. Hi everyone, I'm Tianyi, also from Columbia University. Today I will talk about the special effect spring force cancellation and then give a brief summary to our work. So in addition to the desirable behavior of kinematics coupling and torque-wise decoupling, this paradigm also leads to spring force cancellation. Let's recall from the last slide that red and orange tendons are winded in opposite direction on the motor shaft. Thus, the flexion springs and the adduction springs are counterbalancing each other. The upper left picture is a simplified 1D illustration of this concept. By carefully designing the adduction spring parameters, we can make the resultant torque on the motor shaft small enough to be balanced out by the gearbox stiction. Here we used a plot of resultant torque on the motor shaft to illustrate this concept, as shown in the bottom left picture. The gray line represents the resultant torque and the gray zone represents the motor gearbox stiction. There are two benefits in this scenario for Astrobee robot in the space station. First, it can keep pulse when powered off if the disturbances are small. This is an important feature for the use case in the International Space Station. Since the power is limited there, the hand needs to keep the pulse when turned off. This is especially useful for long-term perching on the handrail. Second, it also allows human intervention if the external forces provided by human operators are large enough to break the gearbox stiction. This is a required feature so astronauts can open and close the hand manually when necessary. We brought this design to NASA Ames Research Center, then finished a number of preliminary integration tests with the Astrobee robot. We tested mechanical, electrical, and the software interfaces, and we also controlled the hand from the teleoperation computer. This video demonstrates the versatile grasp in the Astrobee platform. Here is another video demonstrating a future application for this robot, object delivery for astronauts. In addition, there are a lot of exciting potential use cases, for example cargo bag transportation and even task board operations. In this slide, we summarize our work. First, we formalized an underactuated hand design matrix with 4 design paradigms regarding the choices of agonists and antagonists and tendon routing schemes across multiple joints. We discussed the pros and cons of each design paradigms and showed how hand designers can leverage them to obtain some desirable behaviors. Second, with the ideas from the design matrix, we presented a design combining tendon agonist and the spring agonist on different joints in one underactuated hand, and showed this approach has various beneficial effects, including versatility in small footprints, powerless grip maintenance, and human intervention. Last, we illustrated those concepts on a physical prototype designed for the real-world use case for Astrobee free-flying robot on the International Space Station. Here we want to thank NASA Early Stage Innovation Program and our collaborators in the Intelligent Robotics Group and Astrobee Working Group in the NASA Ames Research Center for their long-term help and support. Thanks for listening.